Hi, Chem students. This is the last lesson in the spontaneity chapter, chapter 16. I also wanted to point out on the previous set of videos, I listed the readings in your Masterton and Hurley textbook that correspond to each of these lessons. I wanted to reinforce that here. This lesson is based on the last couple sections out of that chapter, sections 5 and 6. So we're going to be considering how equilibrium and spontaneity are related to each other. And we're going to be defining a slightly different free energy from what the last set of lessons was about. We're going to be comparing and contrasting standard state free energy, which is delta G with the little degree symbol, and non-standard state free energy, which is just delta G. So let's think about just generally how concentration affects entropy. Look at the picture on the screen. I've got a gas, the yellow is representing gas particles in one volume and then in a slightly larger volume. A valve maybe has opened and that gas is now filling the container. Which picture has the higher entropy? I'm hoping that you might guess the one on the right. The one on the right, the gas is more dispersed, and that means a higher entropy. You can also think about it as just more possible microstates, so that gives that higher entropy by the formal definition. Looks like my picture might be blocking the solution vial here, but in the second set of pictures, I've got a solution. So the solute particles are dissolved in a small amount of liquid on the left and a larger amount of liquid on the right. Which one has the higher entropy? I'm hoping you might guess the one on the right again. Because as we dilute a solution, again, we're dispersing matter and that increases entropy. So bottom line is that entropy increases as these substances spread out, and we know that free energy depends on entropy, and free energy is how we can define or predict the spontaneity of a reaction. So now we're going to flesh out the differences between non-standard state free energy, delta G, and standard state free energy, which is delta G with the little degree symbol. And sometimes you might see both of these with the subscript reaction or RXN. Sometimes that's left off. So standard state free energy. That's what we were talking about in lesson 2 quite extensively. We did some calculations. When we're calculating standard state free energy, we're assuming that the temperature is 25 degrees C or 298 K, and that any gaseous species are at a pressure of 1 atmosphere, and any dissolved species, any solutes, are at a concentration of 1 molar. Now, that is a big assumption, and pressure and concentration, not only is it typically not randomly at 1 atm and 1 molar, but if it's a reaction, concentrations are constantly changing. So it really is way more often than not the case that a system is not at standard state. So let's just think about an example reaction. Zinc metal plus hydrogen ions from an acid are in equilibrium with zinc ions and hydrogen gas. Just thinking about this from an equilibrium perspective, we talked about Le Chatelier's principle in lab, and you guys did in lecture as well. If the pressure of H2 gas or the concentration of the ions, for example, if any of those are increasing or decreased, that's going to shift the equilibrium of the reaction. If we have higher concentrations of hydrogen ions, it's going to shift it to the right. If we have a higher partial pressure of hydrogen gas, that's going to shift it to the left. So that clearly has a big impact on the direction of the reaction, and really what that means is the spontaneity of the reaction. So delta G is the non-standard state free energy. And so when the molarity of the acid is not at 1 molar, or the pressure of the gas is not at 1 atm, we can calculate it to determine spontaneity. And that will allow us to actually predict, is this reaction going to form products, or is it going to form reactants? There's a really key formula that helps us do this. Delta G, non-standard state free energy, equals standard state free energy plus R times T times the natural log of Q. We'll go over each of these terms. So first R, the gas constant. Value we're going to want to use here is 0.00831 kilojoules per Kelvin. We're using kilojoules here because that's what we typically use for the delta G terms. And that Q, that reaction quotient, if you remember back to our equilibrium chapter, whenever you have a reaction A plus B yields C, Q is defined just like K, just like that equilibrium constant. We're just using concentration terms that are not at equilibrium necessarily. When we're calculating Q, gases are inputted as partial pressures in atmospheres. I know some examples previously we might have used molarity for gases just to keep things simple. But in this application, we need to use the pressure of the gas. Solutions have to be given in concentrations of molarity. And then, as you probably recall, liquids and solids are not inputted into the equilibrium constant K or the Q calculation. And so another thing you might recall from that equilibrium chapter is that we use the reaction quotient Q to predict which way the reaction's moving. If it doesn't equal K, the reaction is moving towards equilibrium. So when Q is greater than K, it's moving to the left. If it's smaller than K, it's moving to the right. And if they're equal to each other, that's telling us that our system is at equilibrium. So I'm going to work out on paper this example problem. Using that same reaction we were talking about a little bit before. First, let's do the calculation under standard conditions. And then, here's the new twist. We're going to address the spontaneity of the reaction under a specific set of conditions listed here in the problem. So stay tuned for that.